Well, good morning, everyone. As you can see that we're working still on 15.6. Um, Quite a lot in it. Try and get as much done as we can. This is an example of question 6. I'm very distracted right now because I've got too many windows open. I need to start closing some to give me some room. Okay, that window can all go. Now, if I accidentally close the wrong window in the next 2 minutes, just stay put and I'll come back in. But I have an awful lot of windows floating around here that are just not my friends. Okay, that didn't work. Close him. Getting fewer windows, that's a good thing. What the heck's that? Go away. What about this one? Looks good. Looks good. Do you know why I talk to myself all the time?
No, why?
It's the only way to have an intelligent conversation.
I thought that was going to be a serious answer.
Oh God, you don't know me then, do you? How often? Well, I guess sometimes I do go serious, but more often than not, I'm just being silly. Okay, just making sure I've got everything set up. We are looking good. Okay, so I guess after that little pause, I'm ready. So this is an example from 15.6. It's a triple integral. This is what we're going to integrate. Okay, we've got some more people coming in. And the region E, I don't like E, but I'm sticking to it because they keep using E in this section. I'd prefer R, R is region. It's the letter of the alphabet. Makes no damn difference, but it is annoying for me. So E is enclosed by these two guys, y equals 0, y equals 4. So we got to figure out how to figure out what this region is in terms of the bounds on the x's, on the y's, and finally on the z's. It's quite a messy shape, and I hope I didn't close it. Probably true, I probably did. I put it into GeoBra so I could draw it. And cool, I didn't throw it away. Okay, so I'm going to go in and show you what this whole region looks like to try and justify what I'm about to do algebraically. Okay. So what you're looking at is z equals x squared and 1 minus x squared. No idea why it did that, but it decided it wanted to. Y equals 0 and y equals 4. So when you put this whole shape together, if I scroll out a little bit, I wish the colors weren't all blue, but anyway, these two parabolas, the red one and this faint blue one,
you should be able to click either on the color or on those dotted, the dots off to the side and change the color.
Settings.
Color section, and you can
Gotcha.
change it.
Oh, thank you. There we go. I want something a bit darker. It's too dark. I need something to contrast. Purple. Yeah, purple will do. Right, so should be able to get out of that now. Not fair. Right, you see the two parabolas? They're the z equals 1 minus x squared and the x squared minus 1. Now, when you look at where they interlope or intersect, they're kind of eye-shaped thing. That's the easy one. That tells me z goes from the bottom one, which is x squared minus 1, and it finishes on the top one, which is 1 minus x squared. Now, these two light blue ones represent the y equals 0, y equals 4. and that's fine. So the shape that we're interested in is essentially this chunk in the middle. So it's this eye shape, if you imagine it being like a pipe, and someone vertically cut it here and here. So if you want to visualize, that's what the shape looks like. So now I'm going to try and put some limits on to generate that shape. And we're going to have to put limits on what the X, the Y, and the Z are. Right. So the one I'm calling the easy one is that. And so we have the Z limits. Now I do have a problem here. This guy goes here, this guy goes here, or I swap places. Now, if I looked at my picture, I could tell the positive, the biggest Z value, and therefore the one that goes here is that one, and the smaller Z value goes here. Are you comfortable with that particular who goes first and who goes second? The guy that went like this was 1 minus x squared, and the other guy who went like that was the x squared minus 1. So if you imagine, as far as the z's are concerned, big, small, right? Big, small. Now, the next one's a freebie. Agreed? 0 to 4. No argument about that. Now, the one that's not obvious, the x values. I mean, they have a range, right? If I take my happy face and my sad face, and you imagine going right across there was the x-axis, these two numbers are 1 and -1. But I have to prove them to you. If you take this shape and you imagine it on the xy plane, won't z be 0? Right? On the floor, isn't z 0? And if you say, okay, what happens, what's x is going to look like on the floor? Can you see the plus or minus 1 that I've got? I think the z is easy. I think the y is given to you. Would you agree finding x's is a little bit more awkward? Right?
But the -1 and 1 would have to be true for both. Z is equal to x squared minus 1 and 1 minus x squared, correct?
Yes, and it is.
Okay.
If you want to look at it from a different perspective, couldn't you just make the first z equal the second z? And get the same result? Does that, in your brain, does that make more sense, I guess?
Yeah,
So,
I just wanted to understand that if we had a different problem like this, we would have to make sure that both of them had the same limit.
For sure. And if you did this, that would be verification, I guess. So we're going to do a triple integral of x take away y. The only issues I have really are the order now. So let's figure it out. Based on what you've seen here, would you agree the first one, the one that goes here where my finger is the z's? And so I know the z is going to go from an x minus 1 to a 1 minus x squared. Now these are numbers and these are numbers, agreed? Now in this particular question, once I've done the dz, can you imagine that this expression is going to have x's and y's in it? But since both of these limits are numbers, it's not a big issue. Does the order matter? Not really, but sometimes the working's a little bit nicer with x's first, and sometimes the working's a little bit nicer with the y's first. Based on the fact that this is going to be a polynomial, right? It's just going to have squares and cubes and things in it. I'm pretty sure that there's no particular preference So I'm just, because I want to, doing the X, and I'm going to finish on the Y's. And at this point, can I finish and say, you know how to do triple integrals, you could finish that off in your own time. So construction of the E, the region, and then making sure that you put things in the right order so that when you're finished, you have a triple integral with everything good to go. If you can get to that stage, then every question is pretty much the same question from here onwards, isn't it? It's just do the first variable, plug the numbers in, do the second variable, plug the things in, because they may not all be numbers, and then finally finish with the last guy. And always be on the out for variable separable, in case you can split something apart and just make your life a little bit easier. Any questions about the setup to question 6? Are you comfortable with that one? We good? I will move on then. Okay. Yep. Of course, I had to close one window too many. Never mind. That was 6. Let's look at. This is a version of 7. We're doing a triple integral of a function z. And what do we know? We know that E is bounded basically on one side and then on the other by this fella. Now, where is, there we go. This is a 2, because my 2's look like Z's. If you know me, I put little funny strokes through my Z and I don't put little funny strokes through my 2's, but you can see why I need to, because my 2's are very Z-like, aren't they? So hopefully that didn't distract you. So this says X equals 2. Right now, well, I'm not being very successful. I'm trying to delete these things. Go away. Having issues with GeoBra now. Okay, so what I'm doing right now, well, actually, let's show you what I'm doing right now. I'm going to look at, this is very 3D and very visual what we do. We've got X equals 2y squared plus 2z squared. And I have no, there we go. I'm not having a good day today. Go like that, and you see it's a kind of sideways paraboloid, and then x equals 2 is just a plane. So the shape that we are trying to work with, the region we're trying to work with, is this little bump at the front. You see it? Now, the orientation that we do like 99 times out of 100, don't we tend to project things down onto the floor, the x, y plane, and we use that to decide the limits of the x's and the limits to the y. And the z guys are normally, you know, the things that we work with, right? The z equals function of x and y. Well, this isn't happening here. If you take this shape and you orientate it, let's see if I can orientate it there. Do you see that it's actually not on the XY plane, but we're going to project it onto the sidewall? which is the YZ plane. So that's the geometric reasoning behind what I'm now about to do algebraically. We are going to figure out what the range of X, Y, and Z that would fit the information that they just gave us. And the shape kind of looked like this, didn't it?
Can't see the paper.
You can't see the paper. There. It kind of looks something like that, right? So what do I know about this region E? Well, I need to know what the X's are doing, what the Y's are doing, and what the Z's are doing, right? Because once I've figured that out, we can then set up our triple integral. And we're good. Now, the X goes from 2 to 2y squared plus 2z squared. Now, you can't see my little picture anymore, so I'm going back and looking at it. And you're going to have to trust me on this, but the 2 is further to the right, and the parabola guy is smaller than it. Can you just trust me on that? Because there's a plane here, x equals 2, and then the parabola guy is the x equals fella, right? So that's where they two came from. Now, I need to know the limits, the ranges on the y and z variable. If you go up here and you go here and you intersect these two things together, you will get the x is this fella and x is this fella. Well, when you put them together, you get that. So that's essentially what the projection of that shape would be put onto the side. Do you recognize that as just a circle on well, my orientation is weird. Well, if I orientate it, it looks better this way. Can you imagine it's a circle on the YZ plane? Now, if something is a circle on the YZ plane, we would probably want to do that in terms of polar. Would you agree? You want to do a circle? Polar is the guy to go. But let's put the fellas in first. X is 2. X is 2y squared plus 2z squared with a dx. And my dy and my dz are going to become r dr d theta. So technically, this is going to become an r, and this is going to become a theta now. And it's going to go from 0 to 1 and from 0 to 2 pi. So I didn't even realize that my other two variables, my y, my z, were going to be in polar form until kind of slightly later. This fella is the finish. Now, when you do x's and y's in polar form, isn't x r cos theta and y is r sin theta? Agreed? But what happens if your variables are called y and z? We still have to know what to turn them into in terms of r and theta. Right? Now, which one of these two guys, the y or the z, is like the original x?
The y.
So when you do this guy here, Can you see that you're going to have some x squares and some y squares and some z squares floating about? If you have any leftover pieces, a y will be replaced by an r cosine theta, a z will be replaced with an r sine theta. What you really want to have is, don't you want to just have guys that look like that? Because if you've got a y squared plus z squared, there's a 2 in here, won't that just turn into an r squared, which is much easier? So setting these darn things up is not easy. We're trying to live in a world where we're really not we've really not had a lot of experience in the math world of trying to think of things in 3 dimensions. And I know GeoBrit is a help, but there's still a bit of algebra that we need to. So basically, to do 7, or at least my version, this is the triple integral that is going to work. See who my next guy is going to be. Question 8. They call it a tetrahedron. And it's enclosed by the coordinate planes. It's an interesting phrase. And it's 4x plus y plus z equals 4. So let's explain what they're talking about when they say it's enclosed by the coordinate planes. This guy here crosses the z-axis at 4. This guy here crosses the x-axis. Well, on the x-axis, the other 2 are zeros, so it crosses the x-axis at 1, and it also crosses the y-axis at 1. So the tetrahedron that they are talking about is that shape there. It would look, if I could orientate it a little bit differently. You see, it looks something like that. And we are being asked to find the volume of this shape. So here's a little, very interesting, triple integral property. The triple integral of some region E, 1 dV, is its volume. So you do the triple integral of 1 dV, you will be finding the volume of E. Isn't the double integral of 1 the area of region D for a 2-dimensional? Yes. So that darn guy, we need to set up who E is. Right? Now I could certainly put it into GeoBrit, but all I would see would be a much prettier version of my shape. In fact, it would look really ugly because there'd be planes going everywhere. So I'm not even sure it would help that much.
Interject, but did that 1 come from the coordinates on the x and y axes?
No, it's 1 all the time.
Okay.
So if you do the triple integral of just the number 1, you will get the volume of the region E on which the triple integral is being calculated. So that's it written formally. Such a little thing to know. All right, let's work on this guy. If you look really carefully, there's a triangle on the floor. And the triangle is going to be the guy that's going to get me the X and the Y restrictions. In this shape, Z starts at 0 and finishes at 4. So that was where I got the Z's from. In this region, doesn't Z start at 0 and finish at 4? Right. Now, the floor is a triangle. That triangle, if you orientate it a little bit more in this direction, is this triangle here. I want to find this two-dimensional region because it's going to tell me who the X's and who the Y's are in no particular reason order. And I'll be done. Right, if you want to do this two-dimensional area here, you'll need to know the equation of that line. Are you all comfortable with the equation of that line being 1 minus x? Right. Now, what do the y's look like? Well, let's get the x's out of the way. The x's go from 0 to 1. Now, what does the y's look like? Well, if you do a little random vertical line for the y's, they go from 0 to here. So the y's go from 0 to 1 minus x. We now have and someone didn't notice a mistake I made. This is not 4. This is a rearrangement of this guy. That's much better. If you imagine a random vertical guy going up, yes, he's at 0, but when he reaches the top of the shape, won't it be the Z coordinate in terms of X and Y that you would use? So that was my little mistake. Right, I should be ready to set this thing up then.
How did you get the base of 1, 1 for the X and the Y though?
Oh,
with the 4.
If you take 4x plus y plus z equals 4, and you wanted to know, for instance, where it crosses the x-axis, it crosses the x-axis when y and z are both zeros. Because any point on the x-axis has the property that the x and y coordinates are 0, 0 at that point. And that makes this fella 4x plus 0 plus 0, which is 4, which eventually gets me 1. So that's where that one came from. Now, did I do the y's right? Darn it in space.
That's why I was confused. I thought though.
Yeah, the y value is 4.
Yeah.
Okay, the y value is 4. Darn it in space. Okay, gotta repair this fella. Here goes. That's a 4. Same idea, just a different number. What's the equation of this line going to look like? Well, it has a slope of 4. Right, rise over run. Starts at 4. And it's a negative 4. So it's that guy. So, right, fix that. My method's still the same. I just screwed up with one of my numbers. Right, where was it we were going here? Oh, we were going to set up the question. It's going to be dx or dy, dd, d, somebody, somebody, somebody. I know the z's go from 0 to the top of the shape, which is this. The x go from 0s to 1, check. And the y's go from 0 to the equation of the line, which is now 4 minus 4x. We need to know who goes in. I'm going to give them a name, I guess. Who goes in position 1, who goes in position 2, and who do we finish with? Which one of these 3 range of values should be in position 1? The X's, the Y's, or the Z's?
The Z.
Agreed. And it's going to be Z equals 0 to Z equals 4, take away 4x minus y. Okay, done. Would you agree that the middle one has to be the y's because it has x's in them? So the middle one is going to go y equals 0 to 4 minus 4x. And the top, the last one, if you like, number 3, is the x's go from 0 to x equals 1. And z, y, x is the order that we did that. Are we good?
Professor, I have a quick question.
Yeah.
I kind of missed this part. Where do you find the one for the volume?
It is a miraculous formula that someone else created, and the volume is the triple integral of 1.
Really? Oh, okay.
It is because I mean I can prove it to you relatively quickly. It's this guy here.
No, I just was wondering if the one came from just doing the calculation.
No, nothing to do with that specific question. It's going to be 1 every time. But since we got it, the proof is pretty straightforward. If you imagine that your region D was this nondescript blob in 3D space, if you make the value of it 1, no matter what point you pick, so basically make that 1. If you add up all of these ones, aren't you essentially adding up the volume? Not proper proof, it's a pseudo proof. But I'm going to do another one of these because I made too many mistakes on this one. So I'll just keep the basic format and just choose another one. So let's have the same idea, but it's going to be 8x, 4y, 2z, and it's going to equal, it's going to equal 16. And it's bounded by the coordinate axis. So basically, it's another one of those pictures. So that gives me a chance to redeem myself on the x, the y, and the z. Now, if you look at this equation, where will this plane, it's a 3D plane, basically it's coming down, cutting through the thing and passing it, but we're only going to see where it cuts. And when it cuts, it's going to look like this guy again, right? Which is why it's a tetrahedron, the name you give to a shape that looks like that. Right, where does it cut the x-axis? Well, y and z are both 0. So in this case, x would be 2. Where does it cut the y-axis? Well, these two guys are 0, in which case it's going to be 4. Where does it cut the z-axis? In this case here, it's going to be 8. Do we feel comfortable about how we constructed that part of the picture? Right. Now, in this case, whenever you can use one direction, the XY plane, I will. Let's imagine a random point on the ground going up to the surface. The Z would be 0 on the bottom, and the top would be this fella. But if you rearrange this fella, which I'm going to have to do on the side, but if you rearrange what this thing looks like in terms of Z, well, it's 16, take away an 8x, take away a 4y. That gets me an 8, take away a 4x, take away a 2y. That gives me this fella. So on the bottom, on the ground, the Z is 0. And at the top, the Z is the point on this surface, given in terms of x and y. Are you comfortable how I created that up? Now, on the floor, we have And I'm orientating it differently. You know, when these things, you can orientate them like that because that's the way it is. X is 2. That's obviously the origin. Y is 4. And the triangle region is this guy. If you imagine going this way, X will go from 0 to 2. And Y will go from here, which is a Y value of 0, to here, which is whatever the equation of this line is. Well, this line has a y-intercept of 4 and a slope of -2. So I would be able to tell you that y goes from 0 to 4 take away 2x. Are we comfortable of how these two together generate this piece? Now we have a formula. The volume of this tetrahedron, the volume of any shape, is its triple integral over its region of 1. Now in this story, we have x's, we have y's, we have z's, right? And we have to figure out now where they go in the scheme of things. Z's got the most variables, so he goes right here. So 0 to 8 take away 4x take away 2y. And so dz gets done first. Y goes from 0 to 4 minus 2x. So dy goes second. And x goes from 0 to x equals 2, and that is dx. And this triple integral will be the volume of that 3D tetrahedron. Yeah, I think that went much smoother the second time. Hopefully, is the process cleaner now without the mistakes I made to distract us? Anything about that you want me to go over? If not, we'll start moving on to the next one. Right, so if you're ever asked to find the volume of a shape in so many words, it's going to be the region E triple integral of 1 dV. Okay, I think we'll get time for one last one. And this one is going to be version of question 9. A lot of stuff here. They want to find the volume of a solid. It's enclosed by a cylinder, y equals x squared, and planes, z equals 0, and a y plus z equals 1. Okay, we need to put this package together to try and figure out who E is. I could put this again into GeoBra and look at the thing. It would certainly be interesting to try and imagine what it looked like. Since I don't really have enough time to go out and in. Can you imagine what y equals x squared would look like? Wouldn't it basically look like this on the floor? So when you do an equation that looks like this in 3D, what you basically get, oh God, I'm a hopeless drawer. Can you imagine this shape coming up? It's like a curved piece of paper going upwards, right? like y equals x going on the floor, but going upwards, it looks like that. Now, what does z equals 0 look like? What does z equals 0 look like?
That's just a
XY
plane,
plane.
like a wall in the
Yeah.
in the perspective you drew it, right?
Yeah, I call it a very unmathematical name, isn't it, the floor? Isn't it XY plane? Right. So this guy is essentially the XY plane. So can you imagine this curve going vertically upwards forever? And then somebody says, nope, you stop at the floor. Now this fella is a plane which is like a sloping diagonal plane. So can you imagine that this shape that might look something like this right now? Someone then cuts it with the plane y plus z equals 1. And when you cut through it, can you see that you're going to, when you put this fella in touch with this fella? Right, it starts getting ridiculous, right? Drawing 3D things in 2D paper doesn't help. GeoBra is okay, but GeoBra is actually just 2D television screen of something that's 3D. But I've got enough information to work on it. If you put these two pieces of information together, doesn't that tell you that y is 1? Where does z equals 0 meet y plus z equals 1? Well, they meet when you intersect these two equations. So you put 0 in here, you get y equals 1. I now know what y is. So in my shape here, we got y goes from 1 to x squared. So get that darn picture out of the way. That's a good start. What else do we need to know? Well, I guess I need to know what z does. Well, if I use these two pieces of information, doesn't z start at 0 because of this? And if you rearrange this, you get that guy. So that's how I got the z fella. Now, if we can figure out what x does, and it has to be numbers, we're good to go, aren't we? What does x look like?
One of them would be square root of y.
Okay. And on this side, you get 1, and this side you get -1. If you plugged it into GeoBra and you looked, what does that shape look like when it meets the x-axis? You'll find that on one side, you know the curve that I was talking about, the thing that looks like there, it goes from here to here on the floor. Right. When you are talking, my orientation is weird again. Try that again. When you do the XY axis, the orientation is distracting. But basically, the guy that you're going to do is positive and it's going to be curved in what direction? Like we've done the paper, so it makes more sense to my brain. It's going to be cutting at 1. Oh, good. 1 to -1. Those are the three guys. So I have a triple integral to set up. It's going to be 1 dv. And that gets the volume. So based on the limits of x, y, and z here, we should be able to do it. Right, the last decision. Let's do the easy one. Since the x's are all numbers, won't the x's go from -1 to 1? So that one is done. Right, I got a decision. Do I do the Z values or do I do the, you know, who goes here and who goes there? That's the problem. Which one do you do right at the beginning then? This first one.
I would do the y values because you have an x squared.
I think
Okay.
you need to do the z first, because then when you integrate, you'll get y, and then when you integrate with respect to y, those y's will become x's.
That is the right order. So you will make sure that you do the Z's first. Now, what's that going to get you? Well, it's going to get you some answer with y's in it, like she said. And then you do, after that, you do the y's. And if you do it in that order, won't all the y's eventually turn into x's? And then integrate with x's is a perfect match. If you did it the other way around, if you did the y equals 1 to y equals x squared, wouldn't you get some x squareds? Which isn't a bad thing, but wouldn't you get a y left over when you switch places? Right, there'd be a y kind of hanging out there, which it shouldn't be. Because the whole process isn't it that each time you do it, you get less variables to work with. You don't want to do an order that introduces a variable that's already been taken care of. So Z, Y, and X. So you're going to have some real thought challenges of trying to put restrictions on the X, the Y, and the Z on shapes where the information are described in terms of planes intersecting with second plane intersecting with third plane. So you imagine this one's got a curve going up the way, meeting a floor, meeting a diagonal cut. You put that package together, that's what we got. Well, that's all I have time for. So say hi if you haven't already. And I'm not so sure if we could call this cool stuff, but I could certainly describe it as interesting, difficult, thought-provoking, and visual.
Elegant.
Oh, that's a new word. You like it, elegant. Yeah. That's it for today. Bye-bye, guys. If you have any questions, of course, I'll hang around till later. And we'll finish these guys off tomorrow. I wish I could spend more time. They take forever in the day, but that's the most I can do.
Professor, I had a question about the last exercise. Can you please pull it up again one more time?
Okay, so we're talking about, I believe, this one, right?
Yeah, the one that we just finished.
Gotcha.
I'm trying to understand where you get the lower limit for the y. That's the part that I'm a little confused about.
Oh, this limit here?
Yeah, the lower limit for the y, yes.
Okay, where that one came from. Right, well, I'm going to take two of the planes. This is a plane, right? It's basically the floor.
That's correct,
right?
yes.
Right.
The,
and
the
then
XY
this,
plane.
right, this fella is also a plane, right?
That's correct.
It's like a diagonal plane of some kind. Actually, it's not got any x's in it, so it's basically it's a plane coming vertically downwards, I guess.
Okay.
Now, if you find out where do these two intersect, right? What does it look like when they intersect? Well,
let's say 1.
Y plus 0 equals 1.
1.
So
okay.
Y equals 1. So I just found out, basically I said, okay, if we call these plane 1, plane 2, and plane 3, right?
Okay.
I just found out where plane 2 and 3 intersected, and that told me Y equals 1.
Okay.
Now, suppose I did plane 2 and plane 1. I guess that's a weird order. But if you look at Z equals 0 and Y equals x squared, right?
Okay.
Now you imagine what that guy looks like. Well, can you see my y equals x squared side now?
Okay.
So you're done.
Okay.
Now what about the z's? Well, if you take this fella, which is
Yeah.
z equals 0,
Zero.
and you
Yeah.
rearrange this guy, you get the z fellas, which is
Yeah.
where they come from. The x's are a little bit trickier because what we're trying to do here is, what do you get if you have a y equals x squared, right, which is here, but you put into all the other restrictions like it's on the floor and y is 1 in particular, y equals 1. Well, when you put y equals 1 in here, you make the restriction plus or minus 1. Well, visually what that would look like, if you were trying to imagine what it would be, is y equals x squared looks like that, but when you cut it at y equals 1, you generate those two guys.
Oh, okay.
So that's what the floor would look like. And that's what generates this one and this one.
Okay.
And then there's this guy here, basically, with this guy here, generates the Z guys.
Okay. Okay. All right.
Okay. You got a question?
That helps.
Anyone else?
Me?
Yeah, anybody.
I do.
Go for it.
It's about number 6, which is the first one you did today. Let me pull it up, and which I had done yesterday and landed on mostly on the same process of doing it. So
Okay. I'm trying to find 6, but I don't remember things as well
I can
as
share
used
my
to.
screen. I have it pulled up.
That'll work. Show, here we go.
Okay. So
Now sharing.
okay. The thing about it was, when I got it wrong, I checked my calculations in a triple integral calculator, just like, to figure out if I'd made a calculations error on there. And I did that as well today. And this gives a negative answer, which, is that okay for a 3D volume in some way? Because
if it's a physical volume, it's bad news, but this isn't a 3D volume. This is a triple integral, and in triple integrals, negatives are okay.
They are?
Right.
Okay.
The analogy between the two is, can you imagine Calc 2? When you talk about the area under a curve, right? The area under a curve, that can be 0, positive or negative, and that's okay. Right?
Yeah. I guess I'm just used to like negative area being a sign something is wrong.
Well, the reason why you think of that, and it quite makes a lot of sense, is context is important. If the question in Calc 2 had been not the area under the curve, which is sometimes called the net area, but the question had been, what is this area, right? In other words, a physical area, so, like square inches, in which case negatives would be bad news. But wouldn't you, in those questions, take the bit that's below the x-axis, calculate its integral, and then take its absolute value and make it positive, and then the piece that was above the x-axis, you get its area, and then you'd add them together. Well, when we do physical volume questions, right? What is the volume of this region bounded by? And they tell you lots of stuff. Volume has to be positive because it is a physical thing, right? It's a solid 3D volume. Triple integrals, however, are more closely related to net area, right? Areas under curves. Those could be 0, positive or negative, depending on the situation, the equations that were being used.
Okay.
Does that work for you?
Yeah.
Right.
Weird.
Yeah, but then let's think of it. Imagine you have a 3D region, right? And in this region, it was, at any given point, it was the temperature. Let's say degrees Kelvin to keep the physicists happy, right? So there could well be a lot of points whose temperature is negative.
Well, not in Kelvin.
No, bad choice. In centigrade then. Whoop,
Okay, perfect.
right? In centigrade. There could be a lot, you're right, because it goes from 0 to, what is it, -200, not negative.
Yeah,
but positive
negative
200.
270, not negative, but 273.15.
No, right, so that's the magic number. Right, but in centigrade then, couldn't you have the total temperature being a negative number?
Yeah, you could.
Right? Because in that case, the triple integral isn't measuring volume, but measuring the sum of the properties inside that shape, whatever the property is measuring. You could have, I try to think of something else that has a plus and a minus to it.
I feel like with charge, that it would probably be meaningful to have negative charge, like that could
Right.
indicate direction.
Good analogy. So you got this solid chunk of thingy bob that's got different charges at different points. Maybe on the shell it's positive, but internally it gets more and more negative. And so what you're doing in a triple integral is the total charge. I think it's in coulombs or whatever charge is measured in, right? So that could be negative because you could have a negative overall charge. I think does magnetism have a positive and